So in the next 20 minutes, we are going to cover the whole of sound. So here we go. Shout out if you've got a question, but otherwise it's rock and roll time. We finally got there. So the first thing is that sound is a longitudinal wave. Can you see my writing? Say yes. Good man.
Yes, sir.
I'm delighted. So we have to explore what we mean by longitudinal. What this means is instead of the oscillations occurring up and down like a water wave, the oscillations occur backwards and forwards. So we usually demonstrate this by showing a thing called a slinky spring. You all know what a slinky spring is. And if you squash the spring at one end and then squash it again, and then it gets more spread out, and then it gets more squashed, and then it gets more spread, that is analogous to a sound wave. Of course, a sound wave isn't really a slinky spring. A sound wave is made up of air molecules going backwards and forwards, but the oscillations are in the direction of my arrow. And where there are lots of molecules, we call it a compression, and where there are only a few molecules, we call it a rarefaction. So one wavelength is the distance between two compressions, and one wavelength is the distance between two rarefactions. So we can sum up that C is a compression, and a compression means lots of molecules there. And if it's in air, it means higher pressure. Because we've got lots of molecules, then we get higher pressure in that region. And then this R, it's not called a decompression, it's called a funny thing called a rarefaction. Rarefaction. And that's because there are fewer molecules. You've heard of the expression rarefied atmosphere. And sometimes it's used for being up a mountain. They say the air is rarefied. So it's the same idea. And it's because there are fewer air molecules in that region, and therefore it's a lower pressure. Questions so far? Good. Okay. Well, if we want to make a sound, then if you manage to do that FET video, you'll have seen that what you can do is you can put a kind of loudspeaker here, and the loudspeaker creates a compression and rarefaction because the cones vibrate backwards and forwards. I'm just trying to make my pen a bit thicker. Okay, here's the loudspeaker cone. We're going to see soon how a loudspeaker works. And the loudspeaker goes in and out, as shown by the dotted lines. When it goes forwards, it creates a compression. And when it goes backwards, it creates a rarefaction. So that's literally pushing and sort of pulling the air. And the same thing happens at the other end, where you've got your lug hole, also known as your ear. The drum gets pushed, and then it bounces back, and then it gets pushed, and it bounces back. And amazingly, that pushing and pulling of the eardrum is converted through the genius of the human body into electrical signals that go to your brain, which you can interpret as sound. Okay, so far. Okay,
Yes,
well
yes,
done.
sir.
The distance between two rarefactions is one wavelength, and the distance between two compressions is one wavelength. And remember, lambda is the letter for wavelength, and that's the end of part one. Okay, part two. Sound obeys the wave equation. Okay. Well, we've seen this already. And this is the equation that relates speed to frequency and wavelength. And what it's saying is that if you want to find the speed at which this wave travels, then you take the frequency and multiply it by the wavelength. Now, some of you will remember that the frequency is 1 over the period. So we can also write V equals lambda over T. And it's at this point that we realized that actually this formula is pretty obvious. The wave equation is always written v equals f lambda. But actually, we know speed equals distance over time. Lambda is a distance. Capital T stands for period. It's a time. How long does it take to travel one wavelength? Well, one time period. The wavelength is the length in distance of one wave, and the time period is the length in time of one wave. So the speed is lambda over t, just because speed equals distance over time. So that's the first thing we note. The sound obeys the wave equation, but then the speed of sound in air is usually, we reckon, about 340 meters a second. But a sound can also travel through liquids, which is just as well for whales, otherwise they wouldn't be able to talk to each other. And it travels quite a bit faster. And actually, in solids, it travels even faster still. You see, in air, it's just to do with the random molecules jiggling backwards and forwards in the direction of travel. Whereas with liquids and solids, there are intermolecular bonds. So if you get a squashed bit of solid, it very quickly squashes the next bit. So the speed of sound is much faster in liquids and solids. Now, over the holidays, I wrote a page where you could try and measure the speed of sound. And some of you may have seen it, involving my wife in a high-vis jacket banging two stones together. Well, two bits of wood, actually. Now, this is the speed of sound in air. The speed of sound in air is 340 meters per second. So that means that even if somebody's 340 meters away, the time delay is only a second. And measuring 1 second with a stopwatch is ridiculous. So if we're going to measure the speed of sound, we've got two options. We can either make the distance much bigger, or we can make, well, if we make the distance much bigger, then the time gets much bigger, and we can measure it with the stopwatch. Or we can get a more accurate timer. So it's all very well to say increase the distance, but who's got 340 meter long garden? Nobody. So what we do instead is we increase the distance by using an echo technique, where if here's your house and down here's the bottom of your garden, you've got two bricks banging together, then the sound goes backwards and forwards. And you can say, well, okay, I will time it going backwards and forwards 20 times. You adjust the banging rate until you're banging in time with the echo. And then you time 20 there and backs. So that's one way of increasing the distance. You could use echoes. Get a more accurate timer. Well, that's what I tried to do. I tried to use an iPhone working to the nearest hundredth of a second. Unfortunately, when I copied the document into MP4, the definition went and you couldn't see the numbers on the iPhone. So that was a disaster. But e.g., use a video or an electronic timer. I had super slow-mo with my iPhone. And it was great because you could see the two blocks of wood, these two blocks of wood, you could see them coming together. Because my wife had a high-vis jacket on, you could see the gap in high-vis yellow getting smaller and smaller and smaller in slow-mo. So you could see exactly when the two blocks came together. And then there was a little pause. Then the sound would arrive. And because it was on slow-mo, the sound would go boom. So it was really funny. It was really spooky sound. But anyway, as I say, unfortunately, when we looked at the video, I couldn't see the times in the image that I sent to you. Somebody was talking to me about, I think it was Anders, was talking about using, go away, go on. Anders was using frame by frame to get the time, but I can't see how to do that on an iPhone. He used some other app off the internet so that you could advance it one frame at a time. If you can advance it one frame at a time, that's a really good way of getting more accurate time. Okay, so that's speed of sound. The next thing we've got is loudness, also known as volume. Turn up the volume. And although, as I've said already, sound is a longitudinal wave, we can still draw a graph of it that looks very much like a water wave. Because what we do is we just draw a graph of pressure against time. We could equally draw a graph of number of molecules per cubic meter against time. Go away. I just keep touching the screen. I need to rest my hand on the screen to be able to write. Anyway, here, this is a picture. And all we've got to say about loudness or volume is that a quieter sound would look like this. So louder sound, e.g. a dog barking, louder sound equals larger amplitude. Larger sound equals larger amplitude. So curiously, I've got the colors mixed up. So the larger sound, the louder sound is in black. So there we go, that's louder. We've got two more things to do, so hang on in there and then we'll have questions. The next thing with sound is pitch. Pitch is how high the frequency is. So the pitch, I better get this the right way around this time. Here's our initial sound. And if we want to make it a higher pitch, then we've got the same. Go away. Get out of here. Well, that's great, isn't it? Excuse me a minute while I just get back to where we wanted to be. Oh dear. It's not responding. It's just that my hand's the icon at the bottom there, and I just can't see how I meant to write on the screen without touching it. Here we go. Looks like it's thinking about, maybe what I need to do is just close all these things before I go into OneNote. Oh, look, the back, how marvelous. Okay, so we want to get a higher frequency sound, and we don't want auto rotate. Go away, go on, hurry up, go away. Higher frequency sound, well, we better know that this is pressure and this is time. So higher frequency means it goes up and down in less time. So this is higher frequency. So higher frequency, higher frequency equals higher pitch, which means sopranos as opposed to basso profundo. Oh, go away. Higher pitch. Oh, for goodness sake. Higher frequency equals higher pitch equals lower time period, because period is 1 over the frequency. And, oh yes, we must just slip in here one important fact. Human hearing. You can hear anything between 20 hertz and 20 kilohertz. 20 kilohertz is much higher frequency than even you get on a piano. But part 5 will explain to you why we need to be able to hear up to 20 kilohertz. Go away. Character, go away. I've told you once. Character equals timbre equals style. I don't know how to describe this. I can only describe it by an example. That middle C on the piano does not sound like middle C on a violin. We can tell. And even if they're playing at the same volume, the same loudness, and they're playing the same note, we can tell one is the piano and one is the violin. And the reason is because of the shape of the wave. So this might have the same frequency, but the detailed shape of the wave, detail creates the character. And the frequency of the detail might be anything up to 20,000 hertz. Now, this is why voice recognition software works. The computer stores the character of your particular waveform, and it goes, whoa, that's Mr. Billington. And there you have it.